So hope I am audible to you and you
Yes,
can
yes, yes.
clearly see my screen.
Yes, sir. Yes, sir. Please start. Yeah.
Yeah. So good evening, everyone. Yesterday, I think Dr. UC and my colleague Raunak has spoke about the additive manufacturing. They have touched upon the basics of the additive manufacturing. What are the different additive manufacturing techniques are there? And Raunak, I think, more concentrated towards the EBM and the other additive manufacturing technologies. So today I'm going to talk about additive manufacturing and role of materials engineering basically. So so basically, the users will learn about the what are the different materials are available uh, for the manufacturing through the additive manufacturing route in a material metal side, basically metal AM, and then what are the important properties and selection criteria of AM materials, and then so understanding of the basic AM metallurgy. I will touch upon this topic basically because it's very vast topic again, and also we'll look into more into the defects and how to mitigate this, what mitigation strategies we can use to avoid these defects or reduce the defects. So basically this content has been prepared for 2 hours of session, but I'll try to squeeze it in a 1 hour, and wherever important aspects are there, I will go into the details. And we will have a short question and answer session at the end of the session. So content of this is what influence the material properties, and so metal powders, which is very important ingredient of this metal AM. So I'll touch upon how these powders are getting manufactured, and then metal alloys in LPPF, specifically to the Wipro 3D, and then important LPPF parameters, how this added AM parts has been printed and how they are related to the LPPF, laser powder bed fusion laser parameters basically, that I will touch upon. And then considerations for selection of AM materials. So there are some guidelines while selecting the AM materials that I will talk about. And then what are the common defects, and then what are the mitigation strategies. And if we have to develop a new material, what will be the how we new materials can be developed. That I will go into the details. So basically, when we think about the AM, metal AM, many people ask us how it compare with the casting or other route of manufacturing. Basically, other routes are like casting or forging routes, right? So basically, there is one slide I included in this presentation which will talk about the how AM can be compared with the casting and forging. But here in this slide, I categorized the important parameters of the process which can influence the material properties. Okay, so there are basically and this is divided into the manufacturing stage. So there are 5 important parameters of first comes is the metal powder. So and in this metal powders again there are 5 important parameters. Yeah, so basically the chemistry, as you know, that chemical composition of steel, it's of a great importance since it determines the potential mechanical properties of the finished product, and also controls the degree of corrosion resistance, weldability of the material, and many other mechanical properties. Basically, you might be aware of this. So it's a common, basically chemical composition or chemistry is common for in conventional manufacturing route also. There also it affects the same way. So here one important parameter is particle size distribution, which is specifically applicable to this additive manufacturing. So particle size distribution means these there are the different particle sizes used for the different additive manufacturing processes. So particle size for the MIM and binder jetting is different. Particle size for the laser powder bed fusion is different, and particle size for the electron beam melting EBM is different. So for consistent properties in every build and to ensure the repeatability, it is very important that the chemistry and PSD should be similar. But other than that, however, if both are similar, their third parameters which comes into picture is the morphology. So along with this PhD in chemistry, morphology also needs to be spherical. So I'll show you the some images which from which you will get idea how the morphology of the powder can be assessed. So basically there are different atomization techniques for powder manufacturing, which will result into different morphologies. So plasma atomization can give highly spherical particles and results into good flowability and basically packing density as compared to the other manufacturing routes like a gas atomized powders. And also the reuse number of reuses of the powder shall be tracked. So what happens after every build, powder quality can degrade due to contamination. So, but only using a virgin powder, virgin means it can be used only once, and after that it discarded. So if we have to use this virgin powder, this makes the process not economical, okay, not viable, because because the powder is the main is a major cost in AM. Okay, so basically if we have to use only once, then it will be really difficult to justify the cost. So basically number of reuses, the powder needs to be used a number of 8 to at least for the 8 to 10 number of uses, and then only the process makes process will be uh, feasible, or the per part cost will be less. So, and after that in chemistry, the main important is ONH analysis, basically oxygen, nitrogen, and hydrogen. So these are the non-metallic impurities extremely reactive with the metals like titanium, aluminum, magnesium, like this. So uptake of these impurities can happen at each process steps, beginning with the powder production, its storage and the conditioning of the powder or handling of the powder during the AM process itself. So basically this oxygen, nitrogen and hydrogen can be basically moisture can be absorbed, oxygen content can be increased, so that we need to take care during the handling. When it goes, then powder when it goes to the machine, so there are some important parameters like parameters which defines your material properties. So what are the layer thickness we are printing, what the laser power we are using, so laser speed, hatch distance, scan strategies. So there are different scan strategies can be used, and which gives the different material mechanical properties to you. And then contour parameters, so all these affects basically, and these are very important. Then going to the next stage, which into again into the production, which is a part build here, and how the build layout is, what are the process monitoring tools you are using, what how you are planning the build strategies, that also defines the material properties. Thermal processing, basically so there are different thermal processing processes like stress relief treatment, hip hot isostatic pressing, solution treatment and aging. So basically solution treatment and aging, if it is similar to the conventional, it can be used to the conventional casting and forging routes also. But here stress relief and HIP is specifically, I can say, to the AM. It has to be done, means stress relief is required to reduce the to lower down the residual stresses which gets generated because of the high cooling rates into the AM process. It's inherent in the AM process. Basically, when you are melting the powder with the laser beam, yeah, so micron level melt pools get generated, and these micron level melt pool, they cooled very fast from their melting point. So basically the cooling rates are very high, and because of that, very high residual stresses get generated, and these residual stresses needs to be relieved immediately after the AM process, AM, additive manufacturing, and then only after stress relieving, then only this build has to be removed from the base plate. Till the time the build, whatever the part you have printed will be on the base plate. And then once the stress relief treatment is done, you can remove the part, and then it can be taken to a further processing like hot isostatic pressing, is which is very important step for the aerospace parts. Other sectors like oil and gas and automobile sectors, they are not mentioning this, but in for aerospace parts is compulsory to process through the hip route. And again, solution treatment and aging can be optimized according to the property requirements. And then material characterizations like microstructure, internal defects. So internal defects like porosities, lack of fusion zones. I'm going to show you some of the examples of the porosities and lack of fusion zones, which are the defects, internal defects of the additive manufacturing parts. Then not only the size of these internal defects, but the location of these defects, and then surface characteristics of the AM part. Those are also very important. Then comes the material properties, for example, physical properties of the material, then tensile properties, creep, fatigue behavior of the material, fracture toughness. Basically, on this basis only, your part is going to be judged. So it is very important. The part material after printing or manufacturing through the AM route, it should have a good material or mechanical properties. So going into the details of the metal powders, their manufacturing and tests, and we will touch upon the test procedures. I will not go into the details because I just wanted to give you a feel that there are some test procedures to be employed to assess the quality of the AM powders. So powder is manufactured through the atomization technique. So what is this atomization process? Is it is the is a dispersion of molten metal into particles by rapidly moving a gas or liquid stream. So here you can see the simplistic view of the atomization process. So uh, left side schematic shows the gas atomization process, and whereas the right side schematic shows the plasma atomization process. So first stage of this manufacturing process is the segregation of the raw material as per the requirements, and then the raw material is melted in the vacuum melting furnace. So next stage is the atomization. In this stage, the molten metal is passed through a small orifice to create a molten metal stream. And then this metal stream is broken by a jet of inert gas or water. Okay, if the air is used to break this stream, it is called as a gas atomization process, and if the water is used, it is called as a water atomization process. The size and shape of the particle formed depends on the temperature of the molten metal, rate of flow, nozzle size, and jet characteristics. Here I am showing a very simplistic view, but the process is there are very large number of process parameters in powder manufacturing itself. So basically that rate of flow, nozzle size, jet characteristics, all these can be varied to get the desired quality of the powder. And glass and plasma atomization usually results in a more spherical particles as compared to the water atomization process. So after this atomization stage, particles are collected into the collection chamber from where it is. So here it is collected, and from there it is taken for a segregation according to the size classification. As I mentioned you, each AM process requires different particle size, and after they are blended together to make in a particular size range with respect to additive manufacturing process, then quality inspection is done and the powder sent for the packaging. So why these different atomization processes? So basically there are three atomization processes I spoke about, like water atomization, gas atomization, and plasma atomization. So each process is having some are like some advantages and some disadvantages. So on the basis of that, we can choose the powder through which we process the powder we want for our part manufacturing. Okay, so basically when we are talking about water atomization process, it will give you the very high throughput, and the range of particles, very large range of particle size, but and so it requires a feedstock in the ingot form. So basically it's the powder what you will get is of irregular particle morphology, and also you can see some of the satellites, but the cost of the powder is less. So when you are choosing powder for the automotive parts, you can choose the powder processed through the water atomization process. Then gas atomization, here again there are number of wide ranges of alloys available to process through gas atomization. It's also suitable for the reactive alloys. Basically, water atomization is not suitable for the reactive alloys, but gas atomization can be employed. Yeah, and only requires feedstock in ingot form, and also this is also having a high throughput. And but again, satellites can be seen. Then there is a low yield basically, and also the particle size range manufactured can be is between the 20 to 150 micron. So some these are the some disadvantages also, but one more, the third one is a plasma atomization. So through this process you will have a very good control over the process, and extremely spherical particles can be produced, and it requires the feedstock to be either in a wire form or powder form, which is high cost, and that's why this process is powders manufactured through this process is very high. Cost is very high. So for aerospace sectors, you can choose the plasma atomized powders. So basically, so here is the trade-off. If you want a good quality powder, and if it is for the aerospace and defense applications, you can go for the plasma atomized powders. And if your requirement is not so stringent and application is in the automotive domain, as I mentioned earlier, you can choose the gas atomized powders or even water atomized powders, and in some cases to reduce the cost of manufacturing. So this is a material portfolio available at Wipro 3D for processing with LPBF, laser powder bed fusion. So we have in nickel based alloys, we have Inconel 718, Hastola X, Inconel 625. In iron based alloys, we have SS316L, 17-4 PS steel, 15-5 PS steel, and M300 maragin steel. And in titanium, we have Ti6L 4V grades, grade 5 and grade 23. Grade 23 is ELI extra low interstitial grade, which can be used in medical applications basically. And then aluminum alloy LSI 10 mg. So basically, this is the portfolio available at Wipro 3D, but there is a lot of research going on in a AM space with the different materials, and day by day the number of materials are getting added into the catalog, and yeah, in a near future you can see more and more metals to be added into the list. So we are also working towards the same. So basically, we are also involved in a custom metal alloy development for the additive manufacturing. In the last 2 years, we have developed two materials, A286, which is a heat resistant steel, and SAF250C1, which is a super duplex stainless steel. In last 2 years, we developed the parameters for these two alloys, and now we are processing these both of these materials through the AM. And I can say that in India, we are the only one which are processing these two materials. And now we are working on the development of the alloy named CM247 alloy, which is used into very high operating temperatures. So this alloy can be used into aerospace applications where the temperature can basically a turbine blade applications or nozzle guide fans NGVs. There the temperature can go up to like 1100 to 1200 degrees centigrade, and there this material can be used. So we are working on it, and we are close to the finish development. So in near term, this also can this will you will see this material to be added into the catalog. So, how we assess the quality of the metal powder? So basically, chemical composition. I'll not go into the details because this is very well established. This is there are different laboratories are there which can which can do this for you. So basically, they check the chemical composition with the different methods like inductively coupled plasma, ICP-OES, or inert gas fusion or wet chemical analysis, and also they will an ONH analysis can be checked with the ONH analysis available in the market. So basically, this is more or less well established process and available at laboratories. So more important and specifically for the AM is the particle size distribution, and so particle size, just I'll talk about this so that you can understand what are the different particle sizes used in a different additive manufacturing process. So here you can see laser powder bed fusion requires the particle size into 15 to 63 micron. Then electron beam melting requires the particle size into 45 to 106 micron, and metal injection molding particle size is less than 38 micron. So this particle size distribution can be checked with a two methods. One is the laser diffraction, second one is a sieve analysis. So laser diffraction is more advanced and it can give you the more information. So basically, you when you do the laser diffraction, you will get the micron values. You will get the values for the D10, D50, and D90. So what does this D10, D50, and D90 show? Shown here is if D10 is mentioned as a 20 micron, here it is 19 micron mentioned. So only 10% of particles are below at 90 micron, 19 micron. And when this D50 is 30 micron, then 50% of powder is below 30 micron, then 50% powder is above 30 micron. And then when D90 is 48 micron, then 90% of powder is below 48 microns. So these three, when you do laser diffraction for powder, you'll get three values: D10, D50, and D90, and this is the meaning of these values basically. And so this particle size have a effect in the process. So the coarser the particle size, more surface roughnesses, then low density you will get, and the more porous the particles are. And if the particles are very fine, then again there is a problem because they will have a more cohesiveness, and they will be less free flowing, and issues with the laser interaction, and also if the powder particles are very fine, there is a chances they can absorb the moisture very easily. So handling again handling will be a issue in that case. So basically this particle size distribution will have a bell shaped curve when you test through the laser diffraction curve. And D10, D50 and D90 values are very important to specify this to your powder manufacturer, or powder manufacturer, basically when you are putting a request for the powder purchase. So metal powder, so morphology I was talking about earlier. So here you can see two different image, so part morphology image for the plasma atomization and morphology image for the gas atomization. In case of gas atomization, satellite formation and agglomeration can be seen. Images for some of these defects can be seen here basically. So this is open porosity. Some gas will get trapped during the powder manufacturing, and this type of defect is gets generated. So this will prevent the part from getting full density. Basically when you are printing the part, this open porosity will generate a porosity into the part. So this is a second one. Is the next one is a split cap, and some powder particles will be elongated. The next one is where the powder particles can be elongated. This can be seen majorly in the aluminum powders, and the satellite formation and agglomeration. This is a more common defect in the powders. Satellites are formed when the finer solidified particles stick to the molten or semi-molten surface of the coarser ones. So as a result of in-flight collision, so you are seen in the atomization image. So powders, when the water or gas stream breaks the metal stream, so it the powder these particles are spread. But when the smaller particles are get attached to the bigger particle, coarser particles, this satellite formation can be seen. Okay, and then this the irregular shape and broken particles also a part of metal powders defects. So finally concluding the slide, I can say that what we want is a high degree of sphericity, control particle size, and minimal satellite count, and limited open porosity when which results into excellent flowability, high density, and perfect layer reproducibility. Perfect layer reproducibility is very important, because imagine that we will be printing the parts into the layers of like 20 micron, 30 micron, or 40 micron. So basically when you are printing 100 height part, this 100 height part will be manufactured by spreading 2500 layers of powder layer. So you can imagine while manufacturing these 2500 layers should have a good reproducibility, and that good reproducibility when you will get it only when the your quality of the powder is good. So other than this PSD, morphology, chemical composition, there are three more tests which we call it as a flow rate, apparent density, and tap density. So basically these are simple tests, as I can say, can be done with standard equipments. I'm not going into the details and just give you how and how this test has been done, so that we can save some time and we can go ahead with the next presentation. So basically the flow rate will be measured through a standard equipment. Here you in this test, the time required for a powder sample of a standard weight to flow through an orifice in a standard instrument is recorded. So this test is very simple and it gives you very good indication of the powder quality. So basically, we have to weigh 50 gram of or 150 gram of powder as per there are ASTM standards available. So as per that, we have to weigh the powder and take the 50 gram or 150 gram powder, and then this pour we have to pour into this flow meter funnel. And then when it is flowing, we have to record the time basically. So shorter the time reported for this test means that the powder flows more easily, and if the powder flows more easily means it will have a good morphology. Basically, you can imagine if if the ball is uh, spherical, correct. If you roll it on a floor, um, it will roll faster. If it is irregular shape, then it will not roll, right? So like this, if the powder particle is spherical, then it will flow faster through this orifice. Basically, it will give you indirect indication of the your morphology. And next is apparent density. In this, we measure the mass of unit volume of the powder, usually expressed in a gram per centimeter cube, and determined by the again a specific method as per the ASTM standards. So basically, this is a quick and cost-effective standardized method of characterizing the volume occupied by a given mass of metal powder when poured freely into a calibrated container. So, with these apparent density and tap density are important from the process perspective, because the apparent density is indicated by the when we are putting the powder into the dispenser of the AM machine. We consider for the calculation, we consider as apparent density as a density of the material, not the metal density. So these are very important. And in tap density, we provide some certain number of taps with this equipment, and we measure the tapped density. So we'll look into the factors considered for the additive parameter development work. And so basically this as you learned from the last 2-3 sessions, AM is a layer by layer manufacturing process. So I'm not going into the details, it is already covered into the other sessions. So it involves selectively heating a thin layer of fine metal powder with a moving focused laser, causing it to melt and then solidify. So, so this is what happens at the melt pool level. So suppose this is a powder layer, and when the laser interacts with the powder and melts the powder, a small melt pool gets generated. Basically, it will be if the laser beam is 80 micron laser 80 micron diameter, then melt pool will be in the range of 200 micron or 250 micron. Basically, it varies according to varies as material to material, and then this melt pool will get solidified. So while interacting with the powder, some of the powder also will, because of this interaction, flown away. So basically, this powder particle, we call it as a which are coming out of the melt pool, we call it as a spatter. And this spatter will flow, the spatter particles will flow, and they will sit there, or they will disperse in onto the powder bed at some other locations. Okay, so when the next layer will be sprayed, and when laser interacting with this powder, these spatter particles will obstruct the laser path, and then because of that, it contributes to the defect formation. So I'll we'll see what type of the defects is get generated. So I will tell you what are the important LPPF parameters. So again, here I categorized this LPPF parameters um, into the different section. So parameters, some of the parameters which are related to the beam are laser diameter, laser power, laser speed. Then some parameters related to hatch strategy are like layer thickness, hatch distance, uh, then stripes or chest quality. These are the hatching strategies basically. Then strip width, rotation angles. So each printed layer will be rotated as compared to the earlier previous layer. So basically, if you consider the first layer at a 0, the next layer will be rotated with the 47-degree angle, or in some cases it's 67 also. So and then there are some hatching strategies like skywriting or time of homogenization. These are the basically related to the EOS machines. In other machines can be different hatching strategies can be maybe there, but overall the concept is same. Uh, then there are some parameters called as contour parameters basically, and these parameters are related to your surface finish. So if you are to if you need good surface finish, then you can use a double contour. Otherwise, if there is not much requirement on a surface finish side, or anyway you are going to machine it, then you can use a single contour. And then recoater, here the recoater material, recoater design, that also contributes. There are different type of recoaters are coming nowadays, and which can be related to your considered as an important LPPF parameter. Then again, build chamber. So basically, in a build chamber is a control atmosphere, and there we can use two different types of gases: argon we can use, nitrogen we can use. Um, so this the flow of this gas flow is also very important. So then base plate temperature. So base plate temperature is important because it will if the base plate temperature is high, it can the generated residual stresses are less. So this base plate temperature can be varied material to material. And then type of nozzle. So these are some of the important LPBA parameters which we look into when we are developing a material or anyway, and also with each and every build we have to set these parameters for the manufacturing. So basically, what the parameters I spoke about can be divided into two categories. So first category is the bulk parameters, and the second is the contour parameters. So these bulk parameters basically are directly affects to your density, productivity, stability of the weld, mechanical properties, and microstructure. And whereas these contour parameters, as I mentioned earlier, affect to the surface quality and then minimum thickness and fatigue properties. So during the parameter development, there will be always some trade-off between these different properties. So for example, if you need productivity, you may need to compromise on the mechanical properties. Same with the surface quality. If you need good quality surface finish in as-built condition, you need to compromise on the productivity. So your aim should be clear while developing the parameters, that you want a good productivity, or you want a good mechanical properties, whether you want good surface quality, or what are the fatigue property requirements. And also basically, when you are clear about the requirement, then these parameters can be developed according to the need. Then the real value addition will be there from the additive manufacturing side. So considerations, I'll not go into the details. It is covered in an advanced level. So more important is that we'll see some of the defects, so that you will be aware that maybe all the peoples are talking about the good things about the AM. But I just wanted to give you what uh, what to look for the other side. Basically, what can happen if the or how to assess the quality of the AM parts. That is also very important. So so common defects. There are two most common defects are observed in LPBF. One is a lack of fusion zone, and second is a keyhole formation. So, going into details of how these defects are getting generated, a helpful way to think about this is to plot our parameter choices in a PV space. So, what is this? P is a laser power against the scanning velocity. So, if we scan too fast with the too little power, basically, so then we will be landing in the region of the part which is do not fully melt, leading to a lack of fusion porosity. And if we apply too much power for the chosen speed, then we may overheat the melt pool and causing the deeper energy penetration and leading to an effect known as a keyhole formation. Dr. UC might have spoke about it, but I'm just speaking about this PV space again from the materials perspective. So between these two extremes lies an operating window where we will achieve a good part density. So here the energy from our laser is sufficient to fully melt the powder and underlying metal without penetrating too deeply. So here you can see figure suggests that we can in this figure somebody will think that if we can increase both power and speed together to build faster, but to some extent it is true. However, there is a limit to how hard and fast we can go, right? So beyond one point, so this is the well-pool behavior becomes unstable and we will get a beading effect known as a balling up. So balling up, you might have heard about this into welding, right? Welding also if the parameters welding parameters are not correct, you can see the balling up effect. Similar kind of balling up effect can be seen if the laser power and laser scanning velocity are very fast. And in this region basically. So, and we also tend to see the increase in the spatter formation at a higher laser powers. So, so figure B shows the lack of fusion phenomenon. If we use less power for a given speed, as I mentioned earlier, then the melt pool will be smaller. Now, the lower energy laser energy may not penetrate deeply enough to fully melt the powder layer, and the top surface of the solid metal will be melt, but the below it leaves the unmelted powder, resulting in excessive porosity, and there is a risk of delamination. Basically, these two layers will not get connected, and there is a risk of delamination. And figure number C and D shows the keyhole formation phenomena, where the too much power is used for a given speed and we see excess penetration of the laser into the metal under the layer of powder, and because of this excessive energy the melt pool can collapse on the cavity to form a pore of inert gas at the base. So such a pores may not close as the melt pool solidifies, generating the subsurface porosity in the welded metal. So because of this greater degree of remelting of the layers below, this keyhole formation defects can be seen. And here the defects are shown into the optical microscopy images. Here you can see the lack of fusion zone in a lack of fusion zone unmelted powder particles can be seen, and you can clearly conclude that this is a lack of fusion zone. So powder particles are as it is, they are not melted, and they are as it is. So you can conclude that this is laser lack of fusion zone. And in this optical microscope you can see small porosities of maybe around like 20 to 25 micron. So multiple porosities can be seen, and this is because of the keyhole formation. uh, Then the most common defect is in LPPF is second. Next is gas porosity. So this defect is attributed to the entrapped gas originated from the raw material powders. So as I mentioned in the slide on powder defects, as a gas gets trapped into the powder during the manufacturing process, and during AM this gas is not able to come out due to the faster cooling rates and creates a void of spherical shape in the part. So you can, if you are seeing a very spherical shape porosity into the part, then you can say that it may be because of the open porosity which was available in the powder. And if you are seeing multiple multiple porosity, then you need to assess your powder quality. So not only this, there are other reasons also for this gas porosity. So basically so low melting point constituents like aluminum, magnesium in the alloy may evaporate into gas to form the gas bubbles. But the major reason is this open porosity. Then, other than the gas porosity, lack of fusion, and keyhole formation, there are process-generated porosities also, and these are attributed to the attributed as a process defects. So this defines your control over the additive manufacturing process, and this may be because of the spatter or condensate falls on the bed, and as I mentioned, obstruct the interaction of laser beam with the powder layer. And these defects are randomly distributed. They don't have any pattern like keyhole formation. So these are randomly distributed, but this defines your control over the process. So other than this, so macro cracks can be seen very high. So macro, because of the very high residual stresses built up during solidification of the bulk material, macro cracks can be observed, and you can see these macro cracks by the eyes. And most of the times, build gets failed due to these macro cracks. And then micro cracks is because of the it can be seen only through the optical microscopy or scanning electron microscopy, and this is because of the liquefaction cracks of low melting point phases at the grain boundaries, or local aging or embrittlement in the heat affected zones, or maybe solidification cracking. Solidification cracking, basically when the melt pool gets solidified, the outer layers gets first solidified, and then there are secondary solidification fronts get created, and these secondary solidification fronts will not get sufficient material to after the solidification contraction, and some of the cracks can be generated. So basically, here and the other than that, cracks at grain boundaries can also be seen in some of the materials. So other common defect is a columnar grain structure. So I'm cons so so first I will tell you I'll talk about the anisotropy, and then we will go back to the columnar grain structure. So basically, what is anisotropy? Is changes in a material's physical and mechanical properties when measured in the along the different axes. Suppose this is our platform or base plate, and if we are printing the coupons or test coupons basically into the different directions, like only three directions I'll take for the moment, like horizontal, vertical, and inclined at a 45-degree. And if I test these three types of the coupons in a different direction, I'll get a different results. So basically, the anisotropy is there in every manufacturing process. Okay, if you check if you go through the forging process also, if you test the test coupons into the longitudinal direction and transverse direction, you will get a difference in the property. Longitudinal properties, because of the grain flow, you will get a good properties, and in a transverse direction, the properties will be the less. Similar here also, we will get a different properties in a different direction, but in additive manufacturing it is little evident, and that's why people talk about anisotropy in the AM. But I can say that for concluding the side, anisotropy is there in each and every manufacturing process. So it is there in AM also. For some of the materials it is more, some of the materials it is less. And why it is anisotropy will be there because of the columnar grain structures, and that's why I consider as a defect here. Otherwise it's not a defect basically, but because of the it creates a variation anisotropic property, that's why we can call it as a defect. So basically, why? So here you can see this is a micrograph into the vertical direction, basically in a build direction. So you can see that the columnar grains are aligned in a vertical direction, because when you are melting the top layer, the heat will get transferred to the uh, transferred to the base plate, and these grains are aligned in a vertical direction. This is we called as a columnar grain structures. And basically when you test in this direction, column in a vertical direction, in a direction of the columnar grains, you will get a good properties. And when you in a if you take out the coupon in this horizontal direction perpendicular to this columnar grains, you can see the lower properties, and that's why there is an anisotropy in the mechanical properties. So these are the some of the other defects which are not very much important. So I'll skip this slide, and how these common defects can be mitigated. So when we are processing, melt pool should be stable during solidification. Uh, just a minute, sorry for this.
Sorry to interrupt you, sir,
Yeah.
but we need to wind up because the next session is about to start at 7.
7 o'clock, correct.
Yeah,
Okay,
can
then
request
I'll
you to.
talk about the mitigation strategies only at the moment.
Yes,
So
sir.
basically, build chamber temperature should be as maximum as possible. As I mentioned you, it will help you to reduce the residual stresses. And so basic and a highly purified inert gas should be used, and this has been taken care in advanced systems. Basically, when the oxygen level, so build chamber at oxygen level is above zero point 0.1, you are not able to start the build. So when it goes below 0.1%, then only machine will allow you to start the build. So basically, ideally, it should be free from the oxygen content, but so this is necessary to prevent the oxidation in the materials at a high temperature. So when it goes to the at oxygen content in the build chamber, if it is less than zero point 0.1, then only you will be able to start the build. And the gas flow rate, as I mentioned, we are using nitrogen or argon. If gas flow rate is optimum, it should be optimum. If it should not be a too low or too high. Basically, if it is too low, then the residue will be remain on the build platform, and the spatter what I was talking about. Basically, this gas flow's purpose is to carry away this spatter, whatever the spatter is getting generated, it should be taken out by this gas flow. So if the gas flow is very low, it will not take out that spatter. And if it is too high, then it will take away the good powder also along with the along with it for the from the build platform. So that will result in a porosity in the part. So, and then next one is the stress relieving. Again, as I mentioned, so SLM, so here the cooling rates are very high, and because of that the thermal stresses, residual high built up of residual stresses will be there, and that has to be relieved through the proper stress relieving treatment. So other process like hot isostatic pressing, basically this process is a simultaneous application of high temperature pressure for a specified amount of time, and this process is used for the homogenization. So whatever the columnar grain structure is there, it can be reduced to some extent by this process. And then other than this pollution treatment and again aging, you if you employ this, it will help you to homogenize the structure, and also the properties can be maintained according to our requirement with the variations in the solution treatment and aging. So micrograph, when we check into the, so basically, yeah, we have, we can take one or two questions. Basically, maybe we have, I think,
Yes,
two
yes, yes, yes,
minutes. Yeah.
definitely. So if any of the participants you have any questions regarding the session, we can open the session for questions. You may put it up in chat, or you may even put it up in or unmute yourself and ask.
Yeah.